Greetings everybody, and today we're going to be taking a look at the definition and axioms of vector spaces. So first of all, let's start off with a vector space that we are already familiar with from high school, which is R2 for instance. And what is R2? It's just a set of all these two-dimensional vectors that lie in 2D space. And we know we can describe each of these vectors with some coordinates, let's say x or y for instance. We could also bump this up a dimension to R3. This would be our three-dimensional vectors which have three components. And we can actually generalize this even further by considering Rn, where you would have n-dimensional vectors which you can't really visualize, but nonetheless you can still describe these with some coordinates, x1, all the way up until xn. Those are n-dimensional vectors, and I should probably rub this out because you can't really visualize them, but these are our n-dimensional vectors. Now we want to start taking a look at abstract vector spaces as well, and those vector spaces don't necessarily have these coordinates, so we're very used to thinking about these bunch of coordinates where we can do addition and scalar multiplication as vectors. But if we want to take a look at abstract vector spaces, we need to strip away this idea of having coordinates and components and whatnot, and just thinking about what these elements in the set are and satisfy under certain operations, and seeing if there are any other sets with analogous operations to addition and scalar multiplication that also satisfy the same axioms and properties that our usual Rn has. So to get started, let's call our so-called vector space V that we have so far. Let's just call it Rn just as an example for now. And there's a couple of things I want to mention with this V. First of all, V over here, this is a set. It's a set with no additional structure applied, so think about it as a big bag full of elements, I guess. Now in the case of Rn, what is the set? This is simply the set of all n tuples of numbers, so x1 all the way up until xn, where x1 all the way up until xn, those guys are real numbers. What we have so far is just a bare set with no additional structure defined on it. So if I told you to take two elements in this set and, well, add them together, perhaps you would not know how to do so because I haven't even defined addition on this set yet. This set isn't even a vector space yet, so you can't even call these elements vectors. They are just simply elements in a set with no additional structure. Now, we know that's not what we want our vector space to be. We know we can add vectors in Rn, so we also need to define an additional operation plus over here. So this is the addition on the vector spaces, and you can think about addition as a map which takes two elements of your set V. Notice I'm not referring to them as vectors or the set V as a vector space. This is still a set, so we take two elements of our set V. You can think about it as a Cartesian product, and this sends us to another element in your set V. And this is one important property that our so-called vector space must satisfy. It must be closed under this operation, which means whatever you get out the other end, it must already be in your vector space. So this is called a closure. We also know we can scale multiply vectors. So in the case of Rn, we can make vectors longer or shorter. So that's scalar multiplication, which is this dot operation right here. So this is scalar multiplication. Again, you can think about scalar multiplication as a map, this dot over here. How does this guy work? Well, it takes in the case of Rn, it takes in a real number along with an element of your set of V over here. So you can think about this as the Cartesian product of R and V, and this spits out another element that's already in your set V. And since we want to go abstract with this, we want to generalize this, notice that R is a field. We can replace this R, it doesn't necessarily have to be R, we can replace this with F over here, where F is any field. We often call this the scalar field, and often one says that some set of V is a vector space over some certain field. So in the case of the vector space Rn, you would call this a vector space over R because the field over here is the real numbers in the case of Rn. But in general, you would say a vector space over whatever field this guy is. Okay, so far what do we have? We have a set, we have addition, which is closed, and we also have scalar multiplication over here, which is closed as well. And now on top of these operations, we also need these operations to satisfy some certain conditions. They can't just be any operations that take two elements and spits out another element. We also need them to satisfy a further 8 axioms. But so far what we have so far is essentially what a vector space is. It's a set equipped with addition and scalar multiplication. And this triple over here, this is what's referred to as a vector space. And usually you can suppress this notation into just a V if you wanted to and call that a vector space, as long as you know what the defined addition and scalar multiplication are. So if we just defined it like this so far, we're not quite there with vector spaces because these two operations also need to satisfy a couple of conditions. So let's go through them quickly. Let's take a look at the properties for addition first, and we'll use the example for Rn to come up with these properties. So we can say that for all vectors u, v, and w in our set V over here, if we just take V to be Rn, what can we do with these vectors in Rn? Well, we know that addition is a commutative, which means it doesn't matter which way you add the vectors. It's also associative, so it doesn't matter where you put the brackets. There exists this neutral element, which I'll call bolded 0, just to distinguish it from the 0 in the field F. That's in your set V, such that any element in your set V, if you add it to the 0 over here, you get back your element V. And the final axiom for addition is that for all elements V in your set, there exists what's known as the inverse, this minus V that's already in your set V, such that when you add the two together, you get the neutral element 0 over here. And if you've seen the axioms for a group, you might recognize these four axioms as just being the properties for an abelian group, where for the abelian group V, equipped with this plus operation over here. So this guy, that's an abelian group, or commutative group, you can call it that as well. So these are your properties for addition that we know exist for Rn. So we would also like any general vector space to have these properties as well. And you also got some axioms for scalar multiplication. So let's say for all lambda and mu in your field of scalars F, what do we have? We have that scalar multiplication is associative first of all. So it doesn't matter which way you put the brackets in this expression, it's still the same thing. So V is your vector over here. Now a couple of things to point out as well. I've hidden some multiplication dots in here. So the multiplication between mu and V over here, this guy would be vector scalar multiplication, just like the dot that we have in here. So is this multiplication right over here as well, because mu V, that's already a vector, and here you're multiplying lambda into another vector, so that's again a vector. Over here it's a little bit different because lambda times mu, this is the multiplication on the field of scalars that you have, because we have scalar times scalar, but then this whole thing is a scalar, which when you multiply onto this vector, that's vector scalar multiplication. So some different dots going on, but often it's very clear which multiplication you're referring to just by looking at the expression. So this is the first scalar multiplication axiom. It's associative. We also have that scalars distribute over the sum of vectors, which means if you have this expression, you can rewrite it as a lambda V plus a lambda W. And the same goes the other way as well. Vectors also distribute over a sum of scalars. And the final axiom is that the multiplicative identity 1 in your field of scalars times any vector is equal to the vector. So 1 is the identity in your field of scalars. And these guys over here, those are the axioms for scalar multiplication that we know exist for Rn. So notice in all these axioms over here, we did not talk about a vector as being some kinds of arrow, some pointy arrow in space, which has a direction and magnitude and has components and whatnot. We simply talked about the vectors as elements in a set with operations defined on the set. And we took a look at some of the properties that these elements must satisfy under these operations. And we come up with these properties over here, which we call the vector space axioms. And technically these two closure axioms are included as well. So scalar multiplication is also closed. These two are also included as well. So you have the 8 over here plus the 2 over here. That makes 10 axioms for a vector space. So there's quite a few, but there's a nice way to memorize these. If you've watched Frederick Scholar's videos on this topic, you'll know that there's this nice acronym CANI. So this stands for commutative, associative, neutral element for the 0 over here, and inverse elements for the inverse. So this is CANI for addition. And then you also got ADU for the scalar multiplication. So this is associative. You have two distributive laws, and you got what's known as a unitary law for this 1 over here. So CANI-ADU, very nice acronym to memorize 8 of the vector space axioms, and of course you got these two closure axioms over here, which are pretty easy to remember. And that's pretty much it for the axioms of a vector space. So overall, what is a vector space? A vector space, we start off with the set. Just a bunch of elements with no extra structure defined on it. Then we define 2 maps, addition and scalar multiplication on our vector space, which must satisfy these 8 axioms over here. And then once we have that, this triple V plus and scalar multiplication over here, this is called a vector space. And again, I think I mentioned this before, you can just say, well, V is a vector space, and if you want to be a bit more technical, you can just say V is an F vector space, where F is your field of scalars. So in the case of Rn over here, you would call Rn a vector space, an R vector space, or a vector space over the real numbers. So just a couple more remarks over here. Once you have a vector space, the elements in your set of V, you refer to them as vectors. Sometimes people think about vector spaces as just a set of vectors, but it's better to understand it the other way around. Elements in your set of V are only called vectors once you can make V into a vector space by defining these additional structures over here. And again, in the axioms, we did not talk about tuples of numbers or arrows or anything like that. We only talked about the elements and how they interact with each other. So in general, vector spaces, you don't need to think about them as arrows in space or whatnot. Just simply think about them as elements in a set which satisfy these axioms with these 2 operations here. So that's pretty much all for this video. We're going to be taking a look at a couple of examples next time. But until then, have a wonderful day, and I'll see everyone next time. Bye bye.